Okay, students. Now, this is where I left off in the 9th lecture. I haven't erased any part of it. So we start from right from where I ended in lecture 9 without any erasing. Now, there has been, there has been a small error, and that I should point out first. Now, look at this point. This is M2 here, right? And this expression, you see, it's WFEMGM2, but mistakenly I have written M1 here, which is wrong. So we should change it to M2. You please make this correction. This about M2. So this is the only correction. There was no way I could tell you before. So this is my 1 minus 2xmg M2. Now, what we can do is we play around this equation a little bit, and you see this expression del HR minus T del S0R. Remember, we took P into delta VR is equal to 0. So, if we do that, then this expression can be written as 0 is equal to del GR0. Remember, this will come important, that this del GR0 is essentially del HR minus T del SR. Right? And then you have plus RT ln KD, which I have expressed to you before. I don't know. Yeah, that's KD for you still. And now there is, I don't copy paste, so I do it extempore, and I took the expression like this, exactly like this. But you see an important point. I could also reverse the expression. I could also reverse this exchange. It would change nothing. What it would change is the signs of these values. Why is it important, I'm telling you? Because I want to draw a diagram now, which has been given essentially by Saxena, and I want to show you the diagram instead of doing mine. It can be done the same, where he has taken the reverse reaction. Have you understood? So I will try and adjust to this reverse reaction, so that I can show you the diagram that Saxena initially proposed. Now, we go in steps. Now, this can be written also. This hell with the pens. This. I'll change the pen. So we can also write this as WFEMGM1 we can write this expression. How can I write this expression? I will do it quickly. See, 1 minus 2xmg, this expression, can be written as 1 minus 2 into 1 minus xfe. Because xfe plus xmg is equal to 1. And this, if you remove, then we can write 1 minus 2 plus 2xfe. Right? And so you see this cancels off, so we get 2xfe minus 1. So 1 minus 2xmg is essentially 2xfe minus 1. Now in the original equation that was regressed by Saxena, he has taken the expression as 1 minus 2x, not 2xfe minus 1, but 1 minus 2xfe. So what I'm doing here, I have now taken this. This expression should be, this expression 1 minus 2x ngm1 should be 2x fem minus 1. But I have reversed the sign here. So if I reverse the sign, then there will be a negative w here. Right? So similarly now, I can write w. Now you can see I can do the same thing here. And this will become plus w femgm2 into 1 minus 2x femg2. It would be the same. The expression would be still the same. Only thing, this minus plus interchange has to be done. See, if I had to, why I'm doing this is not because of any manipulation, because I took an expression which is this way, Saxena took the expression is the opposite way. So everything is changed negative, but if I had to do it, then I had to do the whole regression all over again. But I didn't want to do it. So I have kept this expression now. Now in this expression, there is an important aspect. Now, I will erase this part, the top part, so that I can write the new expression. So now, in this expression, I can write this expression now, this way. Del G, my God, these pens are just deserting me. So now I can write del GR 0 plus minus WFEMG M1 into 1 minus 2x FEM1 plus WFEMG M2 into 1 minus 2x Fe M2 is equal to minus RT ln KD. Now I have to give up my black pens altogether. This is the expression now. Now, remember I told you what data do we have from the experiments? We have temperature, XFE M1 and XFE M2. These are the experimental data that I get, or we get. And then we have say 800 degrees centigrade, you have a data, 800 degrees centigrade, you have this data, you have the data, you have the data, and then 700 degrees centigrade, you have another set of data, you have another set of data. Now, you see, you have a set of data for 800 degrees centigrade, you have a set of data for 700 degrees centigrade, and you have a set of data for 600 degrees centigrade. In fact, you all have this data at different temperatures up to 1200 degrees centigrade if you can take the paper of Wiesenhorn. So, at a particular temperature there, this is determinable. This we can find out from the experimental data. This we can find out from the experimental data. And this one we can find out from the experimental data. Why? because you know the value of R, you know the value of T 800 degrees centigrade, you have the value of XNG, XFE M1 and XFE NG M2, you have the values. So these parameters are known. And what parameters need we determine? Which parameters we need to determine? We need to determine this parameter, and this parameter. So the ones in the red are the unknowns, and the ones in the black underlined by blue, these are the parameters that can be found out from the experimental data set. These are numerical values. So now we come to this expression, then if I take this, then we come to this expression, we can write AX plus BY plus CZ is equal to phi, where X is known, Y is known, Z is known, and phi is known. We need to find out A, B, and C. What is A? Delta 0 R1, where X is equal to 1 always. And then we have WFEMG M1, which is B, and WFEMG, which is C. So we have an equation which we have to solve. And this is clearly a linear equation. So, if we then take this equation, and we have, say, so there are 1, 2, 3 variables to be determined, then we should have, for a perfect solution, we should have at least 3 equations to find out 1, 2, 3 variables, just like you solve simultaneous equations. But normally what happens in a statistical analysis, you need to have more equations than variables to make it statistically robust. In other words, it would be wonderful if you have, say, 30 such data at 800 degrees centigrade, you have 30 such data from which you will determine the 3 parameters that you'll be doing. It makes your retrieval calculations, these are called retrieval calculations, A, B, C. So there will be a value and there will be error associated value. These values will become very robust. Have you understood? Very, very robust. This is done by what is called linear least square fit. Linear least squares fit. All of you may be knowing it, but just for the sake of completion of that, let's say we take a variable x and let's take a variable y, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 expressions like this. Now what you want to do, you have, these are experimental points, x versus y. These are experimental points that you found out. Say, for example, in a class, number of attendance versus grade. Number of attendance versus the number scored. So you will not have them on a unique line, but you will have some scatter. So what you draw is a straight line passing through them, so that the perpendicular distance from the points, all points, the perpendicular distances from all points are the same, are the minimum. So if you have a line like this, you see the perpendicular distances will be very large. So obviously the line does not lie here. the line lies here because the perpendicular distances are small. And then you add it up. So because you're adding up to, and you have positive and negative, so what you do is essentially square them up. That is why it's called linear least squares fit. So that the sum of the squares of the perpendicular on the retrieved line is the minimum. That is the best fit to your points. So what you do here is essentially from say at temperature 800 degrees centigrade, you have three variables for the expression. Sorry. You have three variables for the expression. Right? No problem. But say you have 30 sets of data, then you can do a very good statistical retrieval of your values of A, B, and C. And that makes it very robust, very strong. But if you just have 3 or 4 points, then you can have tremendous play of the line, and that doesn't give it very great amount of accuracy. So what you do is you calculate the values of A, B, and C at 800, 700, 600, 1100, 1200. You find out the value of A, B, and C at different temperatures. Have you understood? And then you plot the values. Plot the values of A, B, and C versus temperature. Have you understood it? So you find out A, B, C at 800 degrees centigrade. You find out A, B, C at 700 degrees centigrade. You find out for all temperatures, you find out the value of A, B, C. So for a particular temperature, you get the value of delta G0R, WFE-MGM1, WFE-MGM2, and this part is all known. Right? So using the linear least squares fit, you can then find out A, B, and C at different temperatures. Saxena and Koch was the first person who did this. And here is the diagram that they got. And I will copy it from the book. So please bear with me. I will try to draw it. Just give me some time. It's not very accurate, but it does. For those who are more interested. You can do it in degree centigrade, it doesn't matter, you can do it in Kelvin. Normally all thermodynamic equations are done in Kelvins. And they had done it at that time in terms of calories per mole. You can do it in joules per mole. Calories per mole means R is equal to 1.98717 calories per Kelvin per mole. But if you do joules, then R will be equal to 8.3143 joules per Kelvin plus mole. So it's easy to convert. This multiplied by 4.189 gives you this value. You multiply calories into 4.189, you get joules. So 1,000, 2,000, 3,000 is the values. I will draw it approximately. It's not possible for me to do it more accurately. These are the error bars, and you draw a line like this. This expression is del G is for del G0, which they had found out is equal to 4479 minus 1948 into 10 to the power 3 by T. That's the expression they found out. This is for delta dg0. And for the other ones, these are the equations that was obtained by both Subrata Ghosh and Surendra Saxena in their first paper. At that time, the experiment was limited. There was no data till 1200 or 1000. That data was brought in much later. But at the moment, this was the value. Now you see here. That's a very interesting results. Now you see the problem. See the interesting point. You see, this is the distance between WFEM1, between the two W values at this temperature, at low temperature. If you go to the higher temperature end, the difference between the two values, what does this mean? Now we know that WFEMG is the interaction parameter of replacing iron by magnesium, right? So the amount of energy that you require to replace iron by magnesium or magnesium by iron, remember, we took regular solution formulation, which means that we make no distinction if Fe is replaced by Mg or Mg is replaced by Sp. We don't make this distinction, we make it simple. So it is the energy parameter that is required to replace iron with magnesium. Now you see, this difference between WFEMG in M1 site and WFEMG in M2 site is smaller compared to low temperature where it is larger. Means what? Means that the energy to replace iron magnesium at M1 and iron magnesium at M2 decreases with increasing temperature. Have you understood? Decreases with increasing temperature. Remember, M1 site was smaller, M2 site was larger. M1 site was smaller, M2 site was larger. Iron, which is the larger ionic radius, was accommodated into the M2 site preferentially. Now we see a different picture. What is the picture? That the FEMG values, which were the energy values that were required to replace iron magnesium in between M1 and M2 site, are decreasing, And you can imagine a situation where they will converge to become same. What would this mean? What would this mean? This is the mathematical value. This is a mathematical value. That the WFEMG parameters are, the difference between the two is decreasing, and hopefully at high temperatures there will be no difference. What does it mean? That means that the difference in size of M1 and M2, which was there before, is now becoming so there will be larger ordering of iron and magnesium at low temperature, and as we go to the higher temperature, that small variations when they decrease to become zero, this will mean that there is complete disorder in the system. That means the M1 and the M2 side does not discriminate anymore between iron and magnesium, which means the size of M1 and M2 becomes identical. So Fe by Mg ratio partitioning does not depend on the size anymore. So what I'm trying to say here is that we look at it numerically and try to give it a crystallographic angle to it. A crystallographic angle to it. Have you understood? And have you understood this? So what is important is to realize that these thermodynamic equations that you are being retrieved from experimental data is telling us something about the internal structural variation as a function of temperature in orthopyroxene. And this happens to all minerals. Orthopyroxene is taken and olivine is taken because these are the most simplest to study. Otherwise, it becomes very complex. Say, for example, amphibole, it's very, very complex because there are many octahedral sites. So it's very difficult to model it. So most of the modeling has been done for spinels, what has been done for olivines, what has been done for specific orthopyroxenes. And remember, these are only FEMG-SiO system. FEMG-SiO. There are no other elements involved, no interferences from other elements. So now, there is a decrease in the WFEMG values to higher temperatures, and conceivably the two would converge to a point where it converges. That means the M1 and M2 size difference has almost vanished. So, FEMG partitioning, understand? FEMG partitioning, remember, Fe has a larger ionic radius, Mg has a smaller ionic radius. Now, what is happening from a very ordered, where iron prefers the larger M2 side and magnesium preferring the smaller M2 side, we are going into a situation where iron and magnesium partitioning is no more controlled by the size of the crystallographic positions being occupied by them. That is erased. Have you understood? This means iron magnesium partitioning, even these two elements, which are known to replace each other at all conditions, even their partitioning is not controlled by the size difference of M1 and M2. Have you understood? That is very important. So the distribution of iron manganese becomes more disordered. Like I can tell you what I told before. I'm erasing this. I hope you understand it. I'm erasing this part. What is a disordered exchange? Fe by Mg in M1 is not equal to Fe by Mg in M2, is not equal to Fe by Mg in orthopyroxene. Not. That's called disordered structure. This is what happens here. And what is random random complete disordered structure is Fe by mg is equal to, in M1 side, is equal to Fe by mg in the M2 side is equal to Fe by mg in orthoperoxide. So now, iron by magnesium partitioning in M1 side is in the ratio of the total iron versus magnesium in the pyroxide. Temperature has no more control. No more control. Have you understood? There is no variation in size between iron and magnesium. Between M1 and M2 side. So iron magnesium ordering follows the initial ratio of Fe by mg in orthoperoxide. One of your classmates one day asked me, why is it that we are getting disordered? This is the answer to the question. This is the answer to the question. Now, very importantly, just before I erase this, it's important me to make you think again. Now this expression, you see, G is a function of temperature. WFEMG is a function of temperature. This WFEMG2 is a function of temperature. And here you have an RTL and KD. So iron magnesium partitioning between two sites in the orthoperoxide crystal structure is a function of temperature. We don't take the pressure because experiments were done at 1 bar pressure, so that pressure was not taken into account. If you have to do that, it would require a completely different set of experiments where you keep the temperature constant and vary the pressure. This will give you the variation of WFEMG and G with variation as a function of pressure. But these experiments are not very easy. These are very complicated experiments, very time-taking experiments, and fairly costly. So we come to this situation where this expression now, FEMG partitioning, this partitioning now has become a function of temperature. Now you can take it to before we go into the next, I think I should tell you this now. I'm erasing this expression, this equation. Now you can ask me, what we have seen, the two W parameters converge at higher temperature to a similar value. Why similar value? Because iron magnesium partitioning becomes disordered, because M1 and M2 size difference does not work anymore at high temperature. In fact, the values would converge to 0 if it is ideal mixing. WFEMG values should converge to 0 if there is, because remember, WFEMG, if it is a value other than 0, it's a non-ideal solution. But if they converge to a value 0, then it's an ideal solution. Have you understood? So that is the point now. Why does this happen? Now the question is, you can ask me, sir, why is it that the M1 and M2 side lose their size, or the size difference vanishes with higher temperatures? Now, I will give you a little bit, and then I will ask you to refer to the book Mineral Physics, written by Andrew Putness. I will not refer to your papers, which also deal with the same thing, but you can find this out from the book by Putness. Putnis. Andrew Putness gives you a very good description of what happens to the pyroxene structure at low temperature and high temperature. I will just introduce you details you can read from the book. Please do read. Now what happens if we take a situation low temperature and high temperature? As I tell you, you should read it from the book because it's difficult for me to draw this complex chain. And this is called the C-axis of pyroxenes. C-axis of pyroxenes. So what happens at low temperature, the C-axis is not actually a straight line. It is a crumpled line where these are all SiO4 tetrahedra. These are all SiO4 tetrahedra. Now what happens is, at height in between these tetrahedra, you have the M1 and M2 sites. And you remember, M2 site is between the bases of the tetrahedra, adjacent chains, between the bases, and M1 site is between the apex and the base. At high temperature, what happens? This line, this joining this base, this line, this becomes straight. This becomes straight. So what happens is, you have this scenario. This is how the SiO4 tetrahedron looks like at high temperature, viewed parallel to the C-axis. Have you understood? So what happens from low temperature to high temperature? This crumpled nature of the C-axis becomes straightened. As it becomes straightened, the difference where M1 and M2 is lodged, that area, because you see here, if you take at the tetrahedra, silicon oxygen, this is a silicon atom here, bound by 4 oxygen atoms at the 4 corners. Now, this Si oxygen distance, as I told you, is 60% covalent and 40% ionic. This is a very strong bond. And the adjacent tetrahedra, here it is, adjacent tetrahedra. This is bonding, this bonding is SiO-Si bond. Oxygen, silicon bond. And this is shared by 2 oxygen, this is the 2 arms of the oxygen bond. So what happens is, as the C-axis chain becomes straighter, the tetrahedral positions rotate into a perfect symmetry. So this is a more high symmetry mineralogy, and this is a low symmetry mineralogy. So what happens here, these gaps that you have, they change. And what happens is, the M1 site here position changes in another site where the site expands. And so the M2 site now shrinks and the M1 site expands. So what happens? Remember, we are talking of 2 bonds, silicon oxygen and metal oxygen. What is metal oxygen? Is manganese, magnesium and iron. So magnesium and iron bonded with oxygen, and silicon bonded with oxygen. Silicon oxygen bond is very strong covalent, but not so with the metal oxygen FeO or the MgO bonds. They are more ionic in character. So what happens is, as you heat the orthoperoxene, the C-axis, instead of being crumpled, becomes straighter. Once it becomes straighter, the axis positions of the axis change, and M1 site the M1 site becomes bigger and the M2 site shrinks. So what happens? The size difference between M1 and M2 site decreases when you are at higher temperature, close to about 1000 or more degrees centigrade. That is why WFEMgM1 and WFEMgM2, that difference shrinks till at high temperature it becomes ideal. So, but I will advise you to read this wonderful section written exactly on this topic of pyroxene crystal structure, or the pyroxene structure with respect to high temperature and low temperature symmetries. This is very important. So what I want to emphasize here, I have done this for an orthopyroxene where you have M1 and M2 sides. Now if you extend your mind to a much more bigger global scale, if you happen to melt the pyroxene, now the partitioning of iron and magnesium between the mineral and the melt, that will control the composition of the melt. Yes or no? This partitioning of these cations between the minerals and the melts, they will vary depending upon temperature, because this influences the mineralogy of the mineral in terms of the mineral structure, not the composition, the structure of the mineral. So, and this, the prevalent temperature, the prevalent pressure, the prevalent composition of the minerals will control the partitioning of elements into the melt in a global scale. Now there's the important catch that I wanted to emphasize from the beginning. So when you talk of crust-mantle interactions, where the crust is formed from the mantle, because melts migrate from the mantle due to melting and migrate upwards to form the crust. Remember this, that although these are global scale phenomenon, magmatism at island arcs, mid-oceanic ridge volcanism, the Deccan intracontinental volcanism, intra-oceanic volcanism, the Hawaiian Islands, we are talking in huge, huge scales. But remember, the truth is, the governing principles are at the angstrom levels. That is the crucial message that I would like to convey every time. That although you see these mega events, mega things happening, but the major control factors are mineralogy and thermodynamics. They are occurring at angstrom scales. Have you understood this? This was my wish that I could convey this to you. Now I'm not left with a lot of time for starting something new. But I think we will conclude it, because the next part is very different. We will start talking now of melting and crystallization, actually phase diagrams. I will talk to you about phase diagrams after this. I know many of you have studied binary phase diagrams. Some of you may have learned a little bit of ternary phase diagrams, but phase diagram understanding is fairly complex. And I can proudly say that I'm possibly the last vestige, few last vestige who will tell you this, and I'm sure you know, but I also can reckon from my experience of being a teacher for so many years that maybe we do not know a lot of things which we need to learn all over, especially phase diagrams in relation to melting. Most places it is taught phase diagram with relevance to crystallization. Although melting is the reverse process of crystallization, but it's not very easy. And it's very important for us to understand phase diagram as to how melting occurs. But before I start you to teach melting, I should once again recap as to what happens during crystallization, especially with reference to the change in proportion of crystal with melt. And that is very, very crucial. So I will conclude this by saying that you see a major events, mantle to crust transfer, this major event, or mantle or crust to mantle transfer in subduction zone, this requires major melting events. But those melting events and the compositions of the melts and the constituent elements and their proportions, including isotopes, are controlled at the angstrom scale of that particular mineral. So, essentially, I believe you don't do good geochemistry if you're not a good mineralogist. You have to be a good mineralogist and a good thermodynamic petrologist if you have to understand geochemistry. It's not only plotting diagrams. It's the dynamics of the system which makes it exciting, not the diagrams per se. Thank you.